Listeners, this video brings out brute force algorithm design technique yet again, but this time we address how to design algorithms for solving combinatorial problems. When you use brute force algorithm design technique to solve combinatorial problems, it earns its name as exhaustive search. Therefore, exhaustive search is the name given to brute force method of design of algorithms specifically to solve combinatorial problems. It is called as an exhaustive search. And where exactly we are going to search? We search for the solutions in a big space called search space. So search space will be like this. The extent of the search space depends upon the parameters and the range of parameters. For example, the lower bound and upper bound of the parameters. Okay, the range is big, the search space will also be big. What exactly are the combinatorial problems? Combinatorial problems involves grouping, ordering, or assignment of discrete finite set of objects, finding subsets of a set, and linear programming, optimization programs, and constrained optimization programs, and other things. TSP problem, assignment problem, and there are many graph problems which will come under the category of what are called as combinatorial problems. The solutions for this kind of problem should be obtained by combination of solutions of components of the same problem. Therefore, combinatorial figures out. Okay, the nomenclature is called as combinatorial problems because of the fact that the total solution is obtained by combination of solutions of components of the problem. Okay, anyway, there are many examples: permutation and combination, and finding subsets of a set, linear programming, optimization problems. These are all examples of, there are plethora of examples that we can quote for combinatorial problems. Okay, therefore exhaustive search is searching for solutions literally, because brute force technique involves searching the solutions exhaustively over the search space. And when we start searching the search space, we will find several solutions we are going to find, and there are feasible solutions. We will make a list of feasible solutions and we will select the best or optimal solution. Okay, therefore when we address combinatorial problems by the way of exhaustive search method or by brute force technique, the algorithm will generally generate a lookup table, and the lookup table will contain several solutions, and we need to pick up the appropriate solution, okay, that addresses the given context. Okay, here search refers to searching feasible solutions over the large search space. Of course, the largeness depends upon the magnitude of the parameters, the magnitude of the inputs. What is the minimum value of the input and what is the maximum value of the parameters involved in this. Anyway, it will generate what is called as the lookup table. Okay, we will just address three benchmark combinatorial problems and the problems which are there from time immemorial, and we will just explain as to how exhaustive search method is to be applied. Okay, traveling salesman problem. Of course, this problem needs no introduction. Anyway, it is about a salesman who is intrigued in visiting all the towns, starting from a common town, starting from a particular town or particular let us say metropolitan city. Here there are 4 cities, A, B, C, D. Let us say he will start from A and he has to come back to A only, thus covering a Hamiltonian circuit, and in the melee he has to find the shortest Hamiltonian circuits. Therefore any graph problem which will come as a problem for TSP will definitely contain weights over the edges. The weights could be distances, the weights could be effort, the weight could be anything. Okay, therefore we will see how exactly we can generate lookup table for this, and how exactly we can pick up the correct solution or appropriate solution. Okay, first of all, while solving this problem, okay, we have to generate the circuits. We are starting from A, coming back to A, and we can also do from B and coming back to B. We can also start the circuit from C and circuit from D. So interestingly, the complexity of this particular problem is n-1 factorial. n-1, it's a huge complexity. Anyway, we will exemplify this by solving, okay, the part of the problem, and it becomes some kind of a mechanical approach, because it is a brute force approach. Anyway, graph is here. Okay, these are all the circuits that I can start, starting from A to B, B to C, C to D, and A. Okay, the starting point is involved 2 times. Therefore, we have to consider n-1 vertices, and we should write the intermediate vertices in the dictionary form. Okay, this is one clue while we develop what is called as lookup table. A to B, B to C, C to D, D to A. Okay, A to B is 6, B to C is 3, and C to D is 5, and D to A is 6, and it will come to 20 units. It could be distance, or it could be effort, it could be time, or whatever, applicable to several contexts. Okay, traveling salesman's problem is a common nomenclature given to that, but anyway, the same problem can be context specific. Okay, once again, this BCD is arranged in the form of a dictionary, BDC. Okay, A to B, B to D, D to C, and C to A. You will get a complete dictionary arrangement if and only if the graph is well connected. That means if all the vertices are connected to all the other vertices. Okay, this circuit will give us 28 units, and A to C, C to B, B to D, and D to A, it will give us 26 units. Like this, we can generate. Okay, here it is an example. It is not exactly all the possible solutions that are listed. For the sake of clarity, we have taken only a part of the solution. Anyway, in this particular list, this happens to be the feasible, and this happens to be the optimal solution. Okay, and we can also generate similarly starting from B and coming back to B. Okay, like that we can generate it. It will so happen that the length of this particular table happens to be n-1 factorial. Okay, then knapsack problem is another example of combinatorial problems. Okay, this is given n items of known weights or volumes, like say W1, W2, W3, Wn. These are all the items may be available in a go down, and they will carry some worth or some value. Let's say value 1, value 2, value 3. W1, okay, the item 1 has a value 1 and weight 1, and we are given a bag. We are given a knapsack of a particular units of weight, particular capacity. Okay, this can hold a particular weight, amount of weight, or magnitude of weight, and we have to insert these objects into this particular bag, so that the volume is not exceeded, the weight capacity is not exceeded, and in the melee we will also collect high valued elements. Okay, high valued elements. Therefore, the situation can be imagined something like this. You are shown a go down. There are several things of different weights and different values, and you are also given a bag, and you need to slip into the shoes of a robber. You have to pick up the things and just put it in this bag and go to some distant place, and you pour it down, and you just count the number of items, and you also count the magnitude of values, or how worth they are. You calculate that worth, and anyway the winner is who has collected the maximum valued things in the restrained or restricted capacity of the bag. Okay, this is the problem. Anyway, this will reduce to finding subsets from a set, and it so happens that you are going to find out an optimal subset among the sets. Anyway, if given a set A, the number of subsets that can be generated is called as a power set. Okay, power set of A. Okay, if there are n elements in the set, definitely the power set will have 2 to the power of cardinality of A, or 2 to the power of n if n is number of elements. Okay, the 2 comes from the fact that either an element can belong to the set or it doesn't belong. Therefore, the 2 is here. Okay, that is the reason why 2 comes over here. That means, for an example, if there are 3 elements in a set, if there are 3 things in a go down, if there are 3 valuable things in a particular accommodation, and you can make 2 to the power of 3 subsets, that is 8 subsets. If it is 4, it can be 16. Therefore, this problem is of exponential complexity. This problem is of exponential complexity because the base is constant and the index is a variable. Therefore, it is of high complexity, but when compared to TSP problem, this is of less complexity because it is after exponential complexity comes what is called as the factorial complexity. Okay, anyway, this is about the complexity of the problem. Now we will just see how exactly we can apply the brute force technique to generate what is called as the lookup table. Here it is, null set, and a person doesn't want to take anything because he feels robbery is not good. Maybe he may be a sage. Okay, it generates a null set, therefore it has 0 weight and 0 value. A, the first thing alone, it has 8 weight, 8 kg or 8 units, and it carries a value of 50 units. Okay, B alone, it has 10, and these are all feasible solutions because they are within the weight capacity of the bag, because the total weight capacity or total volume of the bag is 15 units, therefore they are well within this, but these are all the values. Okay, and here this is not feasible, this is not feasible, this is feasible. Okay, this is not feasible, like this, and this is feasible, and this is not feasible, this is feasible, and all of them are not feasible. They are not feasible solutions at all. Therefore, among the feasible solutions, we have here the maximum valued subset. Okay, the subset contains the thing C labeled as C, the other thing labeled as D. That is C and D. C and D can be placed inside this because it doesn't exceed the total capacity of the bag, and once again it will bring us the highest value, 120 plus 100, it gives us 220. Right. Assignment problem. Assignment problem is well known to us. Of course, those who have studied operation research must have come across this assignment problem. This problem is all about assigning n people to n jobs. Okay, the condition is only one person can be assigned to one job, and assigning ith person to the jth job involves expenditure or cost to the company. For example, if the person is artisan, let us say, if the person is well versed with a particular job and we have to assign that person to that job only, then it will lead to incurring a lower amount of cost for the company, for the enterprise. If you do other way around, if you assign a person who is not knowledgeable, who is not well versed with a particular job, then it will cost, it will be dearer to that particular company. Therefore, the assignment should happen appropriately, right? And this is the problem. And exactly, if you want to solve this problem intelligently, there is a method called as Hungarian method. Okay, Hungarian method will take very lesser rounds for the algorithm, while the brute force technique, okay, as justifiably will take more number of steps. Okay, we need to generate what are called as lookup tables. Right. Here is an example. Okay, these are all the jobs: job 1, job 2, job 3, job 4, and person 1, person 2, person 3, person 4. If person 1 is allotted job 1, he is going to cost let us say 5 crores or $5 or whatever to the company. If the same person P1 is attached to J2, he will cost 7 units of money to the company. It is something like this. something like this. Therefore, the problem will appear in the form of a cost matrix. So person vertically, that is along the rows, and J jobs along the columns. Now we can solve this by generating what is called permutations. Okay, permutations. Let us say 1, 2, 3, 4. We will write like this. The meaning of this is job 1 to person 1, job 2 to person 2, job 3 to person 3. Okay, P4 J4, P1 J1, P2 J2, P3 J3, P4 J4. Okay, so it comes along the diagonal. Therefore, it is 5 plus 11 plus 4 plus 8. Okay, it costs 28 units to the company. So now we will start arranging this in a dictionary manner. So 1, 2, 4, 3. So it is person 1 job 1, person 2 job 2, person 3 job 4, person 3, person 4 job 3. Okay, if you go on adding these units that are availed from the cost table, cost matrix, it's going to give us 22 units. And here once again, person 1 job 1, person 2 job 3, person 3 job 2, okay, person 4 job 4 will give us 25 units. Okay, like that, for the want of time, or in order not to make this voluminous, okay, certain things are skipped. Okay, certain exercises are skipped, certain permutations are skipped rather. Okay, it is shown in here in dotted lines. Okay, if we do it completely, it will involve 24 such rows, because 4 factorial is 24. Here we have got, interestingly, the solution over here, and this is the minimal cost. You need to attach P1 with J1, P2 person 2 with job 3, person 3 with job 2, and person 4 with job 1. It will be dearer to the company by 16 units, maybe 16 crores or 16 lakhs or whatever. Like this you have to generate. Therefore, this is a minimization problem, and this is the maximization problem. Okay, this is a minimization problem, this is maximization problem, finding subsets, optimal subsets. Okay, that is available, that can be generated in a set. Okay, all the elements of the sets will come up with a value and a weight. Okay, this is a maximization problem. Once again, this is minimization problem. Anyway, combinatorial problems are generally optimization problems. Okay, I think we have completed the brute force technique of algorithm design. So in the first video, in the first tutorial, we discussed bubble sort and selection sort. Okay, as the algorithms which are designed on brute force technique. In the second tutorial, we discussed about brute force string matching algorithm, and we discussed with several examples. And in the third tutorial, the last tutorial on brute force technique, we discussed how to address combinatorial problems brute force way. Okay, interestingly, it's going to be extensive search over the search space. Okay, the vastness of the search space, they are going to be really vast. Then only you are going to appreciate the algorithms that are designed to address these kind of problems. Okay, the vastness of this search space depends upon the lower value, the lower bound and upper bound of the parameters involved. So with this, we will conclude the brute force algorithm design techniques. Okay, next we will take up divide and conquer. Until then, bye.